next we're going to talk about a linear regression model called ridge regression. It's a very simple modification to least squares. So we saw with least squares that the values in our solution may be huge. They may deviate wildly from the ground truth depending on what the matrix X transpose X inverse looks like. So in general, when we develop a model for data, we often wish to somehow constrain the model parameters. And so in this case, that constraint might take the form of penalizing values of W that we consider to be too large. So there are many models of this form, but they all have this, many of them have this general form where we say the optimal value for the vector W is equal to the vector that minimizes the sum of squared errors. So this is exactly like before, the sum of squared errors of our approximation, plus some penalty term, which is equal to lambda, which is a non-negative regularization parameter that we would have to set somehow, times some function of our model variables, or our model parameters, W. So this is also a positive function that penalizes values of the vector W in some way in order to encourage properties of W that we might want in advance. So let's be more specific. Let's discuss ridge regression. So ridge regression is basically the name of a model of a particular form where we use a particular form of this regularization function G. So in particular, the ridge regression solution uses as the regularization function G the squared magnitude of the vector W. So with ridge regression, we're trying to find the vector W that minimizes the sum of squared errors, plus this additional penalty, which penalizes the magnitude of the vector W that we are going to return. So clearly there's a trade-off between the first and second terms, and this is going to be controlled by the parameter lambda that we set. So let's look at some extreme cases. So for example, when lambda decreases to 0, this second term disappears, and we're simply left with the least squares solution because we're trying to minimize the sum of squared errors. So as lambda goes to 0, the ridge regression solution that minimizes this function goes to the least square solution. In the opposite extreme, when lambda blows up to infinity, we simply set W to the vector of zeros because any non-negative value in W is penalized so heavily, essentially has infinite penalty, whereas the vector of zeros here essentially is penalizing you as the sum of squared values in the vector Y. So we basically, in the limit as lambda goes to infinity, will return the vector of all zeros because we're penalizing a non-negative value infinitely much. Okay, so let's look at the ridge regression solution. It's very straightforward given our previous discussion. We can solve it using exactly the same procedures as we've looked at previously for least squares. So we have our objective function L, which is now the sum of both the squared errors and this additional regularization term, which penalizes the magnitudes of the vector W. Equivalently, we can write that as this vector product plus this additional vector product. So these two lines are equal to each other. Two different ways of writing exactly the same thing. And now the solution, again, is the point of the objective that the vector W that minimizes this objective. Equivalently, it's the vector W at which the gradient of the objective is equal to 0. So again, we have an objective that looks like this, and we're trying to find this point here. That's the point at which the gradient is equal to 0. So we take the gradient of this function, and we find that it's equal to this. We set it equal to 0, and we solve, or try to solve, for w. In this case, we can solve for w in closed form, and we find that the ridge regression solution, the vector w, that minimizes this objective here is equal to lambda I plus x transpose x, that matrix inverse, times x transpose y. So this is the ridge regression solution. Clearly, it looks a lot like the least squares solution. Previously, we saw that as lambda goes to 0, we recover the least squares solution. In that case, this term disappears, and we're left with what we recognize to be the least squares solution. In the other extreme, we saw how lambda, as it goes to infinity, returns to the 0 vector, and that's clear here. As this value, lambda, goes to infinity, this matrix, the inverse of that matrix, is going to be a matrix of all zeros, and that times any vector is going to give a vector of zeros. Okay, so like least squares, ridge regression also has an interesting geometric interpretation that's useful for developing intuitions of what's happening. So we can see that there's a trade-off between the squared error penalty, which is this term here, and the regularization penalty that we add on the vector w, which is this term here. So the way that we're going to write this is in terms of what are called level sets. So we're going to write these two functions as their own independent level sets, meaning they're curves where if you evaluate the function at any point along that curve, the solution is the same exact value. So for example, if we look at lambda times w transpose w, which is this term here, then any point along this circle, if we take the vector w, in this case we're assuming w is a two-dimensional vector, and evaluate it anywhere along this circle, that penalty is going to have the same exact value. And that's clear here because we're basically taking we're taking the magnitude of w squared times some scalar, and any point along a circle is going to have the same magnitude squared. So these circles here indicate the level sets of the penalty that we have on our vector w. Similarly, what we can show, and I'm not going to derive it here, but what we can show is that we can write this, we can write the sum of squared errors term as being equal to this term, which we note involves w, plus some term that does not involve w. And so a quick way to show this is to simply replace the least squares solution with the matrix, with the vector x transpose x inverse times x transpose y, which is the least squares solution. Replace WLS with that matrix vector product in these two locations. Multiply this entire thing through, reorganize, determine what constants you need to add, and what you'll find is that you can get this term back again. So it's a useful exercise. But writing this term as being equal to this term plus a constant allows us to write intuitive level set for this term here. That's given in terms of the least squares solution. So here we have the least squares solution. We can put that here. And then we have this matrix, which takes the level sets and puts them through and distorts them so that it becomes an ellipse. And we get something like this. And so what we ultimately get is that the final penalty is the sum of level sets for this term plus the level set for this term. And there's a give and take between the two. And so we're going to find a solution that's somewhere along this part here. As lambda gets bigger and bigger, these penalty terms get more and more severe, and so we're dragged this way. As lambda gets smaller and smaller, these penalty level sets kind of disperse, and the solution is dragged this way. And then as a function of lambda, we sweep points in between these two extremes for the output vector w, which in this case is two-dimensional. I think I'll talk here quickly in one slide about some pre-processing. So ridge regression penalizes each dimension of w equally, because the penalty is equal to lambda times w transpose w. So each dimension of w is equally penalized. However, if the scale of the dimensions of the matrix X is different, so if one dimension has values that range between 0 and 1 in general, while another one ranges between 0 and 1,000,000, but you think that those two inputs are equally important, then ridge regression is going to penalize weights on the dimension that takes smaller values. So as some pre-processing for ridge regression, you notice that we didn't have this problem with least squares because we didn't put any restrictions on what the weight vector w was equal to. But here, because we want the weight vector to have roughly equal dimensions, we pre-process the data. It's a very simple procedure. We take the matrix X. In this case, we could think of taking the matrix X and subtracting the mean off of each column, which is what this is saying. So take each X and in the jth dimension subtract the global mean of that dimension, and then divide by the variance of that dimension. And similarly, we take the outputs Y and subtract off the mean. And then in this case, we're able to avoid having to add the dimension of ones. This is something that's nice that we don't have to worry about anymore because we've standardized and made everything 0 mean. And also, we don't run into the issue of having different dimensions of our inputs be penalized differently and arbitrarily because of our regression coefficient, because of our ridge regression penalty.